Okay, so I'm doing a talk on fuzz testing. Can you guys read that? Okay, not that there's much there to read. So real quick, I'm going to contrast what a fuzz test is. A fuzz test is in comparison to a unit test. With a unit test, we all know this, you by hand create mock data and test individual functions. Okay, that's awesome. Except that it sucks because it's tedious, it's boring, you miss edge cases all the time. So what is a fuzz test? A fuzz test, also known as a property-based test, instead of writing data, you are writing a generator that produces random inputs. And then what you do is you say, for a given set of random inputs, what is true about this? So if I run it through the function, what can I say is true about the output? And the generator will generate a whole bunch of different permutations, and that's your test. So it's basically 100 tests in one. So to give an example, this is the typical example is to reverse something twice. Yes, this is Elm, and yes, you're not using Elm. It's fine. I will talk at it at a high level so that we still kind of are on the same page. So this is a test where I'm reversing a string twice. So I would say this is a fuzz test. My generator is a built-in generator that will generate random strings. This is my random, or this is the name of my test, and this is an anonymous function. And what this says is, for a given random string, take that string and pipe it in the same sense that a Unix pipe works. Pipe it into the string.reverse function, take the output of that and pipe it into the reverse function again. And then at the end, assert that the double reverse string is the same as the original string. And if we look at what this does, we see that it'll work because that ran fine. Hope they can read that okay. And if we try and break this, so I'm asserting that the string reversed once is the same as the original string, which is obviously wrong. And what this particular library does is it'll do a whole bunch of different strings, but it concentrates, because it's a string, it concentrates heavily on white space and special characters. And once it finds something that doesn't work, it'll start shrinking it until it gets to the smallest possible value that will fail the test. So that's why you see bang space is not equal to space bang. That's the smallest string it could find that would fail this test. So that was a simple example, and then the other part of this will be a more advanced example. So I want you to imagine a very simple view where there's just a button. You push the button and it's going to go fetch some names. And those names can come back successfully or they can fail to come back. So there's probably a spinner and there's an error and all that. So this is all the code required to handle that view. At the top, again, I know this is Elm, but I'll just describe it at a high level. There are 3 actions defined for this view. I could fetch names, they can come back successfully or they can come back unsuccessfully. So that's the failure part. This is the stateful part of that view. So I have some Boolean flag that tells me whether to show basically a loading spinner. I have the names that were retrieved, or I might have an error. That's what that maybe means. It means I could have it or I could not have an error. And then I have this function down here. If you're familiar with Redux, this is your reducer function. This says, give me my current state and an action. And based on what that action was, I'm going to return a new state. So if we are fetching our names, I'm going to flip that flag to true so that I can show a spinner in the view. If those names came back successfully, I'm going to make sure that bit is set to false and set our names. Otherwise, if there's an error, then again, flip the bit to false and put it in the error. There's actually a bug in this code that we're going to find just by looking through a fuzz test. So I wrote a special generator just for this test that says, start with a random first action and randomly generate 2 other actions that follow it. But in a sensible way, right? You wouldn't have fail followed by fail followed by fail. You would have fetching followed by fail followed by fetching again. Like that's the sensible order. So I wrote a generator that'll generate 3 random inputs. So this is a little bit bigger, but we'll get through this. So I say this is a fuzz test. This is my my custom random generator that I'm not going to show the implementation for, the name of the test. And then everything below that is my big anonymous function that says, for a given set of 3 random inputs, I'm basically going to start with a default record, my default state. I'm going to take that state and pipe it into my update function with my first random message, do the same thing with the second message and the third message. So at the end of all that, my end state is equal to a default state after I've hit 3 messages against it. So at this point, I can say, okay, now I have an end state. What is something true that I could say of this end state? Well, one thing that I could say is true is if that last message was a fetch message, then I should expect that is fetching Boolean bit is flipped to true. So if we run this, we should expect to see that this test pass, and it does. And it tested that with a whole different range of random inputs. Okay, so what's something else that I should be able to say is true of this test? Well, I should also be able to say that, look, I'm going to look at my third message, and if that third message is a success message, then I'm going to expect my state to be exactly equal to this. The is fetching bit is false, I have a set of names, and I don't have an error. And if I run this, we're going to see that this fails. And I'm going to focus your attention down here. I basically say what we expected was false, but what we got was false. We expected John Jane, but we got John Jane, so that's good. But we expected the error to be nothing, but the error was actually some error. And right above this line, it gives us, I hope you can read that okay, it gives us the set of random inputs that produce that error. We started with a fetch fail, we then fetched more names, and then we succeeded. So basically I can infer from this that we started with a failure, later we succeeded, but we didn't clear out some error state. And not sure I would have found that unless I had tested this specifically with a bunch of different random inputs. So we go down here and fix this, we say, okay, on fetch name succeed, what I also need to do is blow away the error, no matter what happened before it. And if I run this again, now the test passes. So that's the benefit that fuzz testing gives you, is it finds those edge cases that you may not have thought to find earlier. So that was a simple example, advanced example. Okay, so that's a library called Elm Test. This doesn't just work for Elm. There's other libraries. Just 5 minutes of Googling showed JS Verify and Test Check JS. So I think it's worth checking out if unit testing is kind of a pain on your project, or you have a lot of edge cases. And hopefully that advanced example helps elaborate that it's not just for simple functions. You could actually use it to verify actual business requirements if you wanted to. So that's all I have. I don't have a timer, but I think I have maybe time for 1 or 2 questions.
So you're saying it generates random stuff. What is it actually random, or is it generating essentially a full set of inputs for that area?
No, because there is no full set of strings or full set of integers. So what it does is it'll, based on the data type, if it's an integer, it'll focus heavily on 0 and negative numbers, but some positive numbers. If it's a string, you focus on special characters and white space. It depends on the data type, but right. But it'll produce 100 tests for every fuzz test I write. So this right here, I'm making 2 different assertions. There are 200 tests in this one test right there.
Is that deterministic of the test that you generate?
When you run this, it gives you the seed. So yes.
So it's not that the inputs are random. It's just, it's not that you don't need to worry about edge cases. It's that your input generator needs to, on some level, worry about edge cases. Like it needs to know that 0 is probably going to be interesting for all integer tests. So I'm going to make sure 0 is it.
By default, it focuses heavily on those types of situations. You can give it, in this library specifically, there's a package called fuzz.frequency where you can assign specific weights to certain ranges of values.
Okay, that's cool.
So one thing we've seen with doing these kinds of tests before is build servers potentially hate you because your build can randomly fail in the middle of a whole bunch of successes. You have a random failure, and then if you're not tracking what caused that failure, it just goes back to success, and it looks like a noise, right?
Which is why the seed is important.
Right. So those are the kind of things to keep in mind, is you want to make sure you're tracking things that might come out of this if you're going to utilize it, because that random failure, if you don't have a way to log what caused it, is going to be damn near impossible to reproduce until the next random time when you get the input that caused the failure. Had a name, right? And
that's where I've experienced that before. I have the same problem. Yep. This sounds like it alleviates those problems mostly by focusing on like the natural boundary point, right?
Somebody else has figured out the edge cases.
Right. And realize that you can generate random mock data because all data is composed of primitive types. So you just need to build it up to that point.
Will it actually go through and create units for you? Like you have an object with 5 integers and 7 strings, and it'll up with some easy.
It'll come up with 100 different random variations. And obviously, the bigger the object, the more it misses because the 100 is a finite number, right? But yeah, so that's all we have time for. So I'm going to skip to art. So thanks, everyone, and we'll get to art now.